Okay, so today's lecture is the last in the magnetostatic series, and it's a topic that does not normally get covered in EM classes or even physics classes to any extent, because I think at the end of the day, most faculty are a little bit scared of it. Mu is a lot more frightening than epsilon in the electrical engineering world. In fact, I always used to joke that there are like 3 topics that you could stump any faculty member in the electrical engineering school. Go to any university, and if you really want to stump them, you ask them about 3 things, and you will get like a stymied look on their face. Why does a magnet, a piece of steel, get attracted by a magnet? How does a battery work? And how do women work? So you can try that out on any faculty member. You have my permission. Was that an offensive joke? No. Yeah, it was, a little bit. You can say the same thing about men. So yeah, this is where we talk at least a little bit about magnetism. And we'll give you at least some tools and some vocabulary for dealing with magnetic materials. So let's deal with this first of all. We know from electrostatics, our discussion back then, that electric flux density is equal to epsilon, which we often write as epsilon r, epsilon naught, times the E field. And of course, epsilon r is always greater than 1. And we have a nice way of thinking about that, right? We understand that when you impress an electric field onto an atom, you're going to pull the positive nucleus in one direction and the negative electrons in another direction, kind of like a rubber band, and they'll snap back into place. The pulling of that dipole apart makes a countervailing electric field, which suppresses the total impressed field, and that means that the total electric field will be less than the original proportionality with the electric flux density. Hence, that constant of proportionality is bigger. You'll have a smaller E for the same amount of D field, and you get epsilon r greater than 1. That's easy to understand. There's some subtleties about dielectrics which are very complicated, but that's you don't encounter those materials too often. Magnetic materials are a little bit more bizarre because there are lots of different mechanisms that produce permeability. So lots of different mechanisms. You can have relative permeabilities that are less than 1, which is unusual compared to permittivity. That's another thing that kind of gives people pause. And the other thing is that the range of permeabilities is so dramatic compared to epsilon sub r. Epsilon r is always greater than 1. If you have a solid piece of material, it's usually a single-digit number, a solid dielectric. You can engineer materials so that they have epsilon r's in the 10s or even the 100s, and that's a pretty impressive feat. Mu sub r at certain frequencies can be enormous, in the tens of thousands for certain type of materials. And yet, most materials, their magnetic behavior is minuscule. Very hard to even measure the difference between that and free space. So our corresponding equation for magnetic field, where again we use a unitless mu sub r times free space permeability, 4 pi times 10 to the negative 17th henries per meter. We're going to talk about all the different ways, not all of them, but the most important ones for generating mu sub r. We'll cover about 6 of them, I think.
17,
7. Minus 7. Minus 7. Okay, so the first one we're going to talk about, a very relatively simple one, it's called diamagnetism. We have dielectrics, right? Well, we have diamagnetism as well. And diamagnetism is a very weak phenomenon. So what happens here, let's say I put some material that has diamagnetic response, I put this into a region of space that normally has a magnetic flux going through it, a B field. What the physicists call the magnetic field, what we engineers call a magnetic flux density. Well, the principal physical mechanism for diamagnetism is usually a response by those electrons circulating nuclei that are buried deep in very low orbitals. So, for example, your orbital model of electrons around a nucleus that you studied in chemistry and physics. You have these different orbitals. And in a material, depending on what the material is, if it's a metal, you know that some of those electrons are clinging around the nucleus and others are kind of free in the solid state material to kind of float around almost like a gas. This response is typically due to clingy buried dielectric, buried electron orbitals. And the response that those orbitals have in the presence of a magnetic field is kind of like Lenz's law. Do you remember that from your physics class? The idea is that if you have free charge and you try to impress a magnetic field into that free charge, that charge will start to move to countervail the change in the magnetic field. And these movable electronic charges will create this Lenz's law response. And it's not a very significant response. Because these are bound electrons very close to a nucleus, they'll just make a little countervailing dipole that will slightly depress the B field inside the material. So what that means is that for a given H field, the B field is going to go down a little bit. And it's a attribute of diamagnetic materials that mu sub r is slightly less than 1. And when I say slightly, it's usually 0.999 some other numbers. It's a very weak phenomenon. This is the weakest of all magnetic manifestations, diamagnetism. The unique thing about it is that it results in a negative mu sub r. A mu sub r that's 0.99 something. Some of the most strongest diamagnetic materials, the way that we treat diamagnetic materials, we often say that the mu sub r times mu sub naught is equal to mu sub naught 1 plus the polarizing field with respect to the volume of material that you have. So this is sort of like mu naught, and then whatever the material has in terms of a polarizing field response, we write that as a chi sub v with respect to volume. And for things like bismuth, the material, this has one of the strongest chi sub v's, negative 1.7 times 10 to the negative 4th. That's really strong, and yet it's pretty weak compared to mu naught. 1 minus 0.00017 gives you that mu sub r slightly less than 1. Water is another one. That's a weaker diamagnetic material. And this one is about negative 9 times 10 to the negative 6th. And these are unitless quantities, chi sub v. Yeah, Lam.
When we get problems where like mu sub r is like 1 or something like that, so that means that the H field produces like a very, very small B field? Or?
That's right. The material will slightly suppress the B field. And that will give you an effective permeability a little bit less than 1. It's so little less than 1 that for all the problems that we typically work, we just treat it like 1.
But I'm saying, how's that slightly less than 1?
Well, if so, you could think of it this way. For the same given H through here, there will be a countervailing B field based on Lenz's law, such that this will go down a little bit for the same amount of H field. And that's what makes that a little bit less than 1 in the relative permeability. Like, if you try to impress this B field, you'll get a slight change in the opposite direction due to Lenz's law by those movable electrons buried in orbital, those dense orbitals of electrons.
That's 10 to the minus 7, right?
Mu naught is 4 pi times 10 to the minus 7.
Right.
And that multiplies this unitless number.
So what I'm saying is, like, H is, it's just any number, like H is 10, and then mu is 10 to the minus, or to the minus 7, so then that brings the number down really significantly, doesn't it? Or am I just missing something?
I think you're missing the multiplier here. So the total permeability, mu, is equal to mu naught. If this wasn't there, it'd be free space.
Right.
And then you have 1 part per change in 10,000, decreasing it. This is a negative number.
Okay.
So you get 0.999 some stuff.
Okay.
And that's a slight reduction. But it is very weak. It is a very weak phenomenon. It's not so weak that you can't produce some really cool videos on YouTube. So is anybody connected to the internet on their computer? Go ahead, do a YouTube on floating frog in a magnetic field or floating grasshopper. And what you'll find is there's some people that took some really powerful DC magnets and they impressed that strong DC field, like, even bigger than what you'd experience in an NMR chamber. And for very light animals made of mostly water, they will literally float above the magnetic field. And the reason is when you have a negative permeability, it expels flux. Higher Musil bar conducts flux. It's a lower energy state to have. Somebody just found the video. There's tons of them on there. But when Musil bar is greater than 1, it's a lower energy state to have the B field conduct into the material. When Musil bar is less than 1, it actually expels B field because it makes less energy. It takes less energy to have a lower B field in that material. Yes?
Is there any research or anything on how that affects the animals on a cellular level?
Yeah. Based on what we know, and we've never done this with the human because you're too heavy, but the animals don't seem to suffer any ill effects long term from this. And the reason is it's actually just a slight deformation in the buried orbitals of your atoms. It doesn't cause any chemical changes. It doesn't really cause any permanent changes in the atomic structure. It's really no different than taking, the people that wear magnets on their wrists, bracelets, for some sort of therapeutic value. We've never really observed any long-term detriment, and some people would argue benefit from doing that as well, because there's really no chemical change happening.
No, I was just wondering, as far as, because if it were done on humans, like most of our synapses are electrical, all of our synapses are electric. So I was wondering if it would alter the magnetic field.
There's actually been some studies into really strong magnetic fields used for therapy. Like, there are certain types of mental disorders where the patients actually feel a little better after they sit in through an NMR. But that's getting into a field that I don't really understand. So I would be... That is an active area of research. I do know that. But I couldn't tell you one way or the other. I think a lot of the evidence is anecdotal at this point. It's such a weak phenomenon, this magnetic field. You'll bend currents a little bit in your synapses, for example, but you won't actually disrupt their operation to any degree that we can measure. So anyway, you can see the floating frog videos. And this is the weakest of the magnetism. So let's make a list over here, going from weak to strong. Another form of magnetism is paramagnetism. And this is a different animal altogether. It's stronger than diamagnetism. You can actually get some Musils that are closer to 2 or 3 or 4. And this is another kind of magnetism that you can understand relatively easily with classical analogies in electromagnetics. So what gives rise to paramagnetism? Generally speaking, these are atoms or molecules that have a net magnetic moment to them. And the kind of classic example is like an iron particle. We know that iron, deep inside its d electrons, has an unpaired electron that imparts a net spin to the atom. Remember from your quantum mechanics class that electrons have 2 states, right? Spin up or spin down. And depending on what spin it has, it will impart that similar kind of, it will contribute that to the net magnetic moment of the entire atom. And from a classical point of view, we can model a lot of these atoms and molecules that have net magnetic moments as little current loops floating in space. If you think about a little current loop, let's see, right-hand rule, let's say we have a current floating in space making a magnetic field. By the right-hand rule, that B field is going to come up and the flux line is going to bend in on itself. So I wanted to sketch the flux lines with the proper polarity. It would look something like this. And we all know from our previous homework that the strongest B fields are in the center here, and it falls out quite a bit as you move away from the center. And that these B fields have swirliness close into this current source via Ampere's law. They will swirl and circulate around a current, I, as it goes around. Now, if I were to take another current loop, and let me just bend it. Let's see. How do I want to do this? Let me go off here and make another current loop. Pretend this is an atom that can be modeled as a current loop, has a net magnetic moment due to the spin of the electron. Have a little current loop here. What are the forces that are going to act on that current loop? Well, my current is circulating around in this direction. Coming out of the board, the B field is going down. That means there's going to be force inward, right? So this force is going to be inward. And on this side of the loop, where the current's going into the board, that force is going to be inward as well. So what does that loop actually want to do at that point? If I'm pushing it on both sides, what it's really going to want to do is flip. And that's a very kind of standard result in classical electromagnetics. Current loops will want to flip their polarities with respect to one another. This will actually want to turn, through mechanical forces, into a loop that does this. In this case, the forces would be, I drew the same darn one. Let me clarify that. In this case, the forces are going to be pulling the loop outward, and it reaches sort of a steady equilibrium state. If it's any degree tilted off that equilibrium state, the forces are going to want to push it and straighten it out such that the north and the south are countervailing, are opposite what the original current loop is. Does that make sense? Everybody buy that so far? So in the yeah, go ahead.
Professor, what is the force, the pulling forces produced by?
The magnetic force. So in that case, we're talking about force is equal to charge times velocity crossed into B field. So that's why I was using the right-hand rule there, right? Current, in this case, current's going into the board, B field is pointing down, force is this way. In this case, the current's coming out of the board, B field is pointing down. I'm actually trying to pull apart my loop, which will hold together because of the electrostatic forces of the atom. It's not going to rip the electrons off. Just might deform the orbitals a little bit. And so if we apply the classical model of paramagnetism into a substance that has a whole bunch of little paramagnetic current loops, so to speak, all the current loops are going to statistically align themselves so that the neighbors are opposite, right? This one's over here. This one's going to have the lowest energy state if it's kind of opposite. And then this one's going to be opposite that. And depending on how the electronic structure or the physical structure of the material is structured, you're basically going to get a random mishmash of magnetic materials that each individually have permanent dipoles, but collectively impart no permanent magnetic dipole to the material. However, if you impress the field, you will start aligning them, aligning the loops in a particular direction. And that will actually make a reinforcing material that has a permeability mu sub r greater than 1. So this is how we get mu sub r greater than 1. Slightly less than 1. This is going to be greater than 1, but not by much, because it's still a relatively weak force. Paramagnetism typically varies for substances like that. Let me give a better bound here. It's usually between 1 and 1.1 in the relative unitless permeability. We can see that behavior, but it's still kind of weak. Couple orders of magnitude stronger than our diamagnetism, and in the opposite direction, positive, but still relatively weak. And unfortunately, this is the last aspect of magnetism that you can understand purely by making classical analogies. The next one will be a little bit different, but you can apply a little bit of classical electromagnetics. But from here on out, now we have to start building in more quantum understanding in our materials. So the next one on our list in our tour of magnetic materials, which is a little bit stronger, is something called Faerie Magnetism. And from here on out, what makes the magnetic material stronger is that the atoms and the molecules now have the ability to cooperate with each other and align their magnetic moments cooperatively in kind of bizarre ways that can sometimes lead to mu sub r's in the 5-digit numbers. And in fact, Faerie magnetism was actually the first form of magnetism that mankind ever experienced. The best example of a Faerie magnet is magnetite. This is something that occurs in nature. It's crystalline iron oxide in a particular format. And to understand that, I have to give you a little chemistry about magnetite, because it's very, very interesting. Some chemistry leads to this interesting magnetic phenomenon. So let's say magnetite has this following chemical formula. Fe3O4. There are 4 oxygens for every 3 irons. And of course, you remember from your chemistry class that oxygen is one of these electrically greedy compounds that when it joins up into a molecule with other compounds, it likes to grab precisely 2 electrons. So it has usually a -2 charge and then has to join up with electropositive ions to form salts and crystals. Well, if we were to do the stoichiometric balance of this chemical formula, we'd find the peculiar situation that iron, to balance this out, let's see, 4 times -2, that's -8 charge for this part of the crystal. This would have to be +8/3 of a charge. And you say, how is that possible? Well, the truth is that there are actually Fe+3s and Fe+2s in various quantities sprinkled throughout the electronic material. You only have integer charges on these electrons. But the crystalline structure allows you to sprinkle Fe2 pluses and Fe3 pluses in such a way that you can match up all the charge with the oxygens. In fact, iron, as we discussed earlier, has a buried electron with unpaired spin that usually imparts a net magnetic moment to the atom itself. And if you go in and study Schrodinger's equations and solve it numerically, as the analytical chemists want to do, the numerical chemists, you would find that the Fe3 plus and the Fe2 plus have slightly different net magnetic moments. So I believe the Fe3 plus is maybe a little bigger. This is the permanent magnetic moment that, if this was an iron gas, would be kind of randomly distributed in every single direction, imparting no net magnetic moment to the material or the gas itself. However, this is not in a gas. This is in a crystalline solid. And what's more, the rules of the solid, of forming the crystalline solid, force these two ions into a spatial and electronic configuration that do impart an electric dipole moment to the material that is permanent and can also be changed with high Muse of R. So how does that happen? I'll give you a quick one-dimensional sketch. Keep in mind that this is actually going on in a three-dimensional lattice in the electronic material. But what will happen is that the Fe3 plus will occupy one part of the lattice, and it'll have a net magnetic moment pointing up. And the Fe2 plus will be the adjacent one, and there'll be intervening oxygens to kind of guide this crystallization procedure. And that will have a oppositely polarized but slightly smaller magnetic moment. This is classically allowable, right? Two adjacent magnetic dipoles will want to orient themselves opposite to one another to minimize the total amount of magnetic energy. We just saw that with the loops. And so this is classically allowable. And so, classically speaking, to minimize the energy of this system, we should also have the neighbor pointing opposite to this one. And then the neighbor, Fe2, should point the opposite of that one. And then the neighbor, Fe3 plus, should point the opposite, and so forth and so on. So in trying to minimize the local magnetic field, you can see what we have accidentally done. We have imparted a net magnetic moment to the material that can be moved around, provided these are all cooperating with one another. And that's solely due to the asymmetry in magnetic dipole moment of these individual ions. They're made of the same stuff, but in these different electronic configurations, they have different magnetic dipole moments. And when you position them in such a way in the crystalline solid, you get a net magnetic moment. And this is why if you get a piece of magnetite out of the ground, it will actually you can pull it up to other metal and other magnetic materials, and it'll stick to it. It's not a very strong magnet, but the Muse of R can be significantly greater than 1. We're talking like the tens. And there are some other variations of this, Faerie Magnetism. And in each of these cases of the type that I'm talking about, we have this unfortunate trait that the word FER appears in all these forms of magnetism. And of course, the reason for that is that this comes from the Latin word for iron, ferrous materials. You can see the chemical symbol for iron comes from that exact same word. And because iron is sort of the first and easiest observed carrier of magnetic forces, all of the words that talk about magnetic behavior start with FERR, but they really have nothing to do with iron. There are other materials and configurations of materials that include amalgams of iron or no iron altogether that still exhibit Faerie magnetism. or ferromagnetism, or anti-ferromagnetism, or all this kind of collection of magnetic behaviors. Yeah?
So if you want to increase the magnitude of this magnetism in a ferric material, so how do you do that? Just increase the magnetic field?
Well, if you wanted to make, what would make the best Faerie magnetic material? It would be a crystalline behavior that forced two different ions with the most dramatic difference in their dipole moments. And that's tricky to do because you've got to have something that forms the proper lattice, usually a cubic type of lattice in the solid state material. They've got to be asymmetrical, but they're not so asymmetrical that this will influence the position of this one. So there's kind of a subtlety there. And that's why we don't see that many that many crystalline salts that exhibit strong Faerie magnetism. Sort of have to have Goldilocks conditions in your crystal to get this to work out just right. Well, let's see. That's getting stronger. Now, the next one is sort of the really strong one. This is ferromagnetism. You change one letter, but you vastly change the performance of the materials. This is the one where you get super huge permeabilities in the hundreds, thousands, 10,000s. And to understand this one, how this material operates, you have to delve into the quantum electrodynamics of the solid state material to even a greater degree that you've understood Faerie magnetism. So let's go ahead and do this. I think you all have enough background to understand the concepts from your physics class. And it's really not that hard. But it involves a very subtle behavior of the wave function of an electron in a solid state material. So let's go ahead and do that one. So for ferromagnetism, again, you start out with materials in a solid state metal that each of the atoms has a net magnetic dipole moment, usually because there's a buried d orbital that has an unpaired electron. Iron is a great example, but there are actually a lot of those kind of metals, neodymium, cobalt, nickel, a lot of materials in the periodic table that have or can have that kind of electronic configuration with a net magnetic monopole or dipole moment. And again, let's draw a linear, simplified diagram of the material. So in this case, we usually have a pure metal, meaning only metal ions are present. No oxygens, no salts, no electrically negative materials. And so if you remember your solid state materials class, which I think you cover in 3040, right? A little bit of that. You remember how metals or semiconductors made of a pure single type of atom, silicon, germanium, what have you. If you put them in a bulk material, they form a crystalline lattice, and most of the electrons cling to essentially one of those points on the lattice, which are occupied by the electropositive nuclei. And then there are some free electrons. They're just kind of floating around in a gas. They don't really belong to any atom. They're in that conduction band. So let's just, for the sake of argument, use iron as an example. Here's the iron atom. And it's going to have bound electrons floating around in here, including that unpaired one that imparts a net magnetic moment. And you remember the craziness of quantum mechanics, that really there's no such thing as a well-defined position of the electron, right? There's a distribution in space. A distribution in space that's probabilistic. Even the bound electrons, so to speak, have a wave function that kind of peaks in probability around atom number 1, but will actually have islands of higher probability around the other nuclei. Even though there are bound electrons, they can actually spend a little bit of time here, a little bit of time here, a little bit of time here. Right? We're kind of familiar with that quantum craziness. And of course, this one will have that same unpaired electron that can sometimes spend a little bit of time here, a little bit of time here, a little bit of time here. And the question is, how do you get these things to cooperate? Because in a ferromagnetic material, what happens is that these unpaired electrons cooperate in such a way so that all of their spins are aligned, every single one of them, which completely flies in the face of classical electromagnetic theory, treating these as little loops of current. If they were loops of current, they should alternate, and because they're all the same, they won't even make a Faerie magnet, let alone a ferromagnet. But there's something else at work here that's very interesting. Do you remember the Pauli exclusion principle in your physics class? What did that say? Anybody were brave enough to volunteer an explanation of that? Yeah, go.
No two electrons can occupy the same space.
Yeah. That's right. That's why you got to have spin up and spin down if you have two electrons in the same orbital. You can't have more than two electrons in the same orbital. And that principle is at work even when you're talking about electrons that share positions with other atoms. And so we have basically two types of wave functions, probability functions with respect to space that can decide the positions of these electrons. Let's say, for sake of argument, that this atom is already resolved to be spin up. It has an electron that's spin up. What are the two choices that we could write with this wave function for the bound unpaired electron in the next atom over? Well, you could have a spin down. And I think I need another color maybe. Well, I don't have another color. Well, I'll try to do this maybe with dashes and dotted lines. Oh, that's right. You've got the colored expos. I apologize to the video students. These don't show up very well. But I think you'll be able to get enough of a distinction. Let's say I had choice number 1. I could make this spin down. By the Pauli exclusion principle, that means that the wave function for the probability of this spin down electron has a peak, highest peak, where the bound electron should be to its home atom. But there will be an island of probability around the second atom. And it will have a fairly high probability because it's spin down and it can inhabit the same state as the spin up electron. And presumably this is symmetric. So that's the blue one. The red one the island of probability is such that because it's in the same state, it has a very low probability of sharing position with the electron that has the exact same spin state with respect to one another. Well, 6 in one hand, half dozen in the other. All things else being equal, you would expect maybe the opposite state in classic electromagnetics to dominate, the spin-down state, because we know that this will reduce the local magnetic energy in the system. But wait a second. These electrons also have charge, right? They're both negative, and they electrostatically repulse one another. This red state, even though it tolerates a slight increase in magnetic energy, will reduce the electrostatic repulsion, because an electron that spends a lot of time in its neighboring state will want to go back to home, so to speak. It takes energy to bring electrons close to its neighbor. And so there's a difference in energy that you get because of electrostatic repulsion in this type of system compared to the minimization of magnetic energy. And that difference in energy is called the exchange energy. And this is basically electrostatic energy in the electron minus the magnetic energy, or really just the difference in energy between these two states in quantum mechanics, the parallel spin and the opposing neighboring spin. And if the exchange energy is positive for a system, that's, again, takes some Goldilocks conditions, right? You've got to have paramagnetic materials. They have to be just the right length apart. They have to have just the right wave numbers with their electrons that are bound. But in certain situations, that exchange energy is positive. And what that means is that this magnetic dipole moment at this location has to line up with this one, with its neighbor. Which means that this one also has to line up with its neighbor. Which means this one also has to line up with its neighbor. And all of a sudden, everybody's cooperating in the three-dimensional crystal of the metal, the solid-state structure of the metal. Everyone operates in unison. That's how you get these really, really powerful magnets with huge Musils. Because every time you impress a magnetic field, in order to minimize the energy, every atom changes its magnetic moment in unison. And that's how you get a ferromagnet. And there are different games you can play. Iron, in and of itself, if you put it together, can make a magnet, a ferromagnet, because they'll all start to cooperate. You can also start to add and dope and sprinkle in different other types of metals that will tweak that exchange energy and create even more powerful magnets. I won't pass it around quite yet because we're not to the point of discussion where I can talk about it, but I have some neodymium rare earth element magnets. These are some of the strongest magnets on Earth. And they're made with the neodymium and a few other elements kind of doped in with the ferrous material. There's huge exchange energy, huge cooperation, so much so you can almost hardly get it off metal. And I'll go ahead and pass that around in a second. How do you destroy a ferromagnet?
Heat?
Heat, exactly. What does heat do? Thermal energy, if you put thermal energy into the material, the atoms, the solid state structure starts to jiggle around more, right? There's more kinetic energy in the system. And it erodes this behavior. It weakens the exchange energy. And it comes to a point where you're jostling the system so much where this no longer happens and the system will revert to a pure paramagnetic state. If you cool it down in the presence of a full in the presence of a magnetic field, what will happen is that you'll align those states, and again, you'll make a permanent magnet. In fact, this is ferromagnets exhibit a sort of peculiar behavior called domaining. Not all ferromagnetic materials have a permanent dipole moment. According to this, they should, right? They should always be pointing in the same direction. I'm not sure if I introduced this concept earlier, but in a solid magnetic material, the work, the energy stored in the magnetic field, is equal to the volume integral of the magnetic field squared, divided by mu. So, in the natural world, you're always trying to minimize B field. in order to minimize the total energy of the system. Again, this is why high mu sub r materials conduct flux and mu sub r is less than 1 actually repel flux. Because if this is less than 1, or less than free space permeability, you'll want to expel the B field in order to minimize the energy. This is a small number. You're dividing by a small number that enhances the work. If this is a big number, then you're going to want to draw your magnetic field into the material. Because this is a big number, regardless of what this winds up being, you can tolerate an increase in B field and still minimize your work in that scenario. Now, the process of domaining in these magnetic materials, let's say you have a piece of iron. It's actually a ferromagnet, but there are these regions inside called domains where they have individually permanent electric magnetic dipole moments, but they arrange themselves so that all the flux is circulating internal to the material. And in this way, you can keep the work of the system much lower than if this was one solid piece of cooperating material with an external return path for all the flux. Does that make sense? If you look at this equation, having a whole bunch of flux outside the magnet takes a lot of energy. So you will actually make a domain wall. The material will set up domain walls, which take energy, but not nearly as much energy as this. And in doing so, you will circulate the flux inside the material. If you impress an external magnetic field, you'll get a strong response, and these domain walls will actually move. To conduct flux through them. And in so you still get the high mu sub r behavior, even if you can't observe the permanent magnetic moment. In fact, there are often crystalline impurities in here that once you move the domain wall, you pin it. It can't move back for whatever reason. There could be some impurities in here that keep it from forming back in its original position. And so this is how, if you ever take like a piece of steel and you stroke it with a magnet, or you heat it up and you cool it in the presence of a magnetic field, you can turn something that didn't have a permanent magnetic dipole moment into something that does. And again, this is just another manifestation of this peculiar ferromagnetic property. Any questions so far? Perfect understanding? Yeah.
What determines mu sub r? Like,
mu sub r?
how do you have like a ferromagnetism like compared to anything else?
Yeah, so the general people, the way that we define mu sub r is that you have a B field and you have a corresponding H field, which is 1 times H. And then if there is any other dipole moment formed by the material itself, sometimes that dipole moment aligns itself with B. Other times, in the case of diamagnetism, it's actually a negative number. And so what we do is we impress a magnetic field, we measure the response of the material in terms of H, and we lump those two things together, and we call that mu sub r. There should be a mu naught out here.
So it just depends on...
Yeah. One parameter, experimentally measured, vastly different physical phenomenon that give rise to it. So you can kind of think of it as an empirical parameter. But that's basically what it's relating to. Yeah?
So what are they doing with the super cool magnet?
And they super cool. Oh, yeah. So one of the reasons why iron magnets get all the publicity is that it's one of the few materials that operates at room temperature below its Curie temperature. The Curie temperature of a magnet is the temperature that once you heat it up past that temperature, the exchange energy goes to 0 or less, and you lose the cooperative ability between the atoms. Well, it turns out there's a lot of magnetic materials that exhibit ferromagnetism, but they happen at room temperature. They are above their Curie temperature. So if you supercool them, they drop below the Curie temperature, they start cooperating with one another, and you get these powerful magnets that form. So I'm not familiar with any supercooled magnets, but I'm sure there are some that are maybe even stronger than our neodymium rare earth element magnets. But you just got to cool them to, liquid nitrogen temperatures or below in order to experience that behavior.
Yeah, maybe. I guess I wasn't clear. Like I saw when I came here the first time, I went to like the MSC department, and they like super cooled some like plate, and they put like a cube on top, and it was floating.
Oh no, that's a high temperature superconductor. They poured the liquid nitrogen on a ceramic material, and then the magnet floated above it. And what that is, that's actually similar to a diamagnet, except the entire material is almost, in a superconductor, almost behaves like that Lenz's law repelling gas. So there's a peculiar state in superconductivity where once you get to superconductivity temperatures, the electrons all cooperate with one another, and they cooperate in a way that makes a Lenz law gas. So they repel perfectly all magnetic flux. And in doing that, you can actually put a permanent magnet on top of that material, and it'll basically float, because it doesn't want to get any closer to the material, because it would have to accept flux into that superconductor material. It just kind of floats there. There are even some peculiar magnetic superconductive materials that are ceramic and have channels of superconductivity in them. They're not solid superconductors, but they have channels of superconductivity. And these type of materials, if you put a magnet close to them, the flux lines get caught in between the channels. And not only do they float above the material, but if you pick the magnet up, the material also picks up. They literally, you can't get in or out any further. The flux lines are trapped in these channels of superconductivity.
I like to see that.
That is also a lot of YouTube
They have videos on YouTube. Yeah, I was about to say, like, they have a little racetrack and actually set up little cars that are set up that way so you can push it and it just follows the track perfectly because of magnetism.
Okay, that's cool. So that's the other YouTube thing you should look up after the end of this lecture. Superconductivity magnet. You probably get tons of videos out of it. I have not seen the race car track one. That looks like fun.
They actually got a board too. Like someone actually stood on a board that was powered that way, or made that way.
Great.
Boards.
Yeah, that's pretty neat.
Back to the Future.
Yep.
2015.
Very cool.
I have a question though.
Yeah.
When you induce a magnetic or create a magnet essentially using and as you just discussed, like changing that field and causing a permanent magnet using another magnet. Is that in like the same way that I think it's called like hysteresis or?
Yeah, hysteresis. Ferromagnetic materials often exhibit hysteresis, and it's directly a function of this domain wall pinning effect, where you impress on it a magnetic field, you shift the domain wall around, and it gets trapped, so that when you take the magnetic field away, the permanent magnetic dipole moment of the material does not go away. It's stuck in a state. Until you put a really strong magnetic field in the opposite direction, then you'll have enough energy to move it, the domain wall, and it gets pinned somewhere else. And then you take the magnet away, and you've got the opposite permanent magnetic moment. Yeah, very good tie-in. Good question. Okay. Now, when you want a high permeability material, a lot of times what you'll do is you'll take this ferromagnetic material. And the problem with ferromagnetism is that it's usually a metal, right? Metals have conductivity. And so they usually, by a Lenz law, they also have eddy current. So if you put this like in the core of a transformer, that's where you want a high permeability material. If you just put solid iron there, it would stink, because you would get lots of Musil, so lots of magnetic flux shared through the metal. You could wrap your coils around that and make a good transformer. But you'd also lose a lot in terms of eddy currents. Because remember, if I have an oscillating magnetic field in a material, I will also make ohmic losses. And so what you find in those types of materials, especially in the transformer coil, is that they'll break up and laminate the iron. So you have a sheet of iron or a rod of iron, a little bit of insulating material around there, and then another rod and another rod. Another thing that you will also see is that the material could be made out of little iron particles that are individually ferromagnetic, but sprinkled into a plastic that insulates the particles from another. So you can't get currents that get set up, eddy currents in the material when you impress an oscillating field on them. But you can still get relatively high mu sub r. I actually have a material like that. It's made by E.M. Cummings. I have a magnet attached to this. You can even peel back the little spacer. It's a little sticky, so don't go too overboard. You'll get your hand all sticky. But this is an example of a rubber material or a plastic material that has iron filings sprinkled up into it. You see it's actually very magnetic. This tracks the magnet pretty well. Then people have used this for like putting RFIDs, tags, like those inductive tags on there, and getting them very close to metal, which you normally would not be able to do. So you can go ahead and take a look at that. Now, that material is not it's an interesting material to play with, but there's a problem with our magnetic materials, and that is, how did we get stronger and stronger mu sub r's? By having materials in an electronic state that cooperated with one another. So in terms of a DC magnetic field, this is how you do it. The higher you want to go, the higher down the list you got to go here. However, a lot of times we're interested in alternating current fields, AC fields, oscillating fields. In my field, with radio waves and microwave fields. And here's the fundamental problem with magnetism at those frequencies. The same mechanism that gives you big mu sub r is cooperation, and that's the same mechanism that makes it difficult to change the orientation of the magnetic field. And so what you will find is that there is a corresponding frequency limitation for each of these that goes down with respect to frequency. So in other words, if I want to see diamagnetic behavior in this dielectric material, I probably go up at terahertz and see that fine. I'll see a mu sub r that's a little bit less than 1, and the behavior will still be there. Paramagnetic materials, well, I could go up into microwave frequencies and see these kind of weak type of mu sub r behaviors. And then they'll suddenly fizzle out. There's a cutoff frequency that you can't go beyond. And in fact, if I go to Faerie Magnetism, I'd find that cutoff frequency, I can get mu sub r of 10, 20, something like that. Cutoff is a lot lower. And down here in ferromagnetic materials with atoms that are cooperating quite a bit, I find that the cutoff is extremely low. Most iron core transformers, for example, wouldn't work beyond excitations above a few tens of kilohertz. Luckily, power is at 60 hertz, right? So you don't have to worry about that. But if we were to graph the material, there's a famous graph in magnetic theory that says if you look at log 10, the frequency, and you plot that log 10, the relative permeability on the y-axis, what you would find is that those, if mu sub r was 1, then log of anything, base anything of 1 is 0, you would find this would persist forever. You could get free space permeability without a material. Slightly elevated mu sub r will have a very high cutoff frequency. Increasing the mu sub r will lower the cutoff frequency. And if my DC mu sub r is really high, like it is in a ferromagnet, then the cutoff frequency is really low. And in fact, this curve here of the relationship between cutoff frequency and the DC permeability of the material, this is often called, I'm not making this up, the Schnook limit. This guy named Schnook was the first to observe this. I think it was out in the 50s. So some schnook came up with this limit. Very powerful theory. and observation. Yeah?
Is it strictly, is it linear?
In the logarithmic domain, yeah, it is. It's I think it's a 1/over relationship in the linear domain. In other words, the only way to see microwave magnetic behavior is if you start out really, really small. Now, there are a couple ways that kind of you can get around that. One is to make some nanoparticles that have a special distribution of their diameter. Turns out if you take a ferromagnetic material and you get that chunk of material somewhere in a sweet spot between, say, 10 and 30 nanometers of diameter, that particle becomes what they call a super paramagnet. My students used to joke and call this super paramagnetism, and then they always add expialidocious. Yeah. So you would fit well in my lab. You have the mentality of an 8-year-old. So what's happening there is that the particle is in this kind of peculiar quantum cooperation state where all the particles inside the little particle are cooperating. All the atoms are cooperating with their magnetic moments, but you can change them really easily because there's not enough of them there to make this critical mass that you have to reverse the polarization and then swing it back. So it kind of has the frequency cut off of a paramagnet, but it has the mu sub r of kind of like a crummy ferromagnet. And those are kind of interesting materials that people are actively researching now, because if you could make materials like that, you would have surfaces that you could lay antennas down almost exactly on metal, and they'd still perform well. We can talk about that behavior later. But that's sort of like the holy grail, to be able to make cheap materials in plastic that you could lay antennas down on top of, and would actually work at UHF and microwave frequencies. That one material that I'm passing around, those are not engineered nanoparticles, so they fizzle out in the higher UHF bands. It works well, but you can't get 10 gigahertz type behavior with a significant mu sub r.
You put the magnet and watch it stop that.
Oh no.
It's working now.
Oh, okay.
Hello, hard.
That's a close one, Anya. Good. Yeah, be careful with the neodymium earth element magnet. I'm going to pass around another magnetic assembly here that's related to that, except instead of a solid suspension of material, it is a magnetic liquid. Anybody ever seen a ferrofluid before?
Yes.
In your high school class, maybe?
YouTube.
Well, a ferrofluid is a suspension of ferromagnetic particles in oil with a little chemistry additive. You've got little ferromagnetic particles, usually made of iron. So we put Fe here. And these are just ground up chunks of iron, microscopic in many cases. And then you put that in a suspension of oil. So this blue pen, and I won't label it oil, but these circular dots are supposed to be oil particles. And normally this type of material would be pretty boring, because if you put a magnet up to this fluid, what would happen? All of the iron particles would go to the side of the magnet, and then you just have oil left over. Boring. Boring. So instead, if you add some surfactant, and what a surfactant molecule is something that has basically two types of bonding hands to it. An ionic bonding hand that can grab onto particles like this, the iron, and a kind of covalent bonding hand that's good for grabbing onto the oil. And so what that makes is a suspension where the whole fluid moves as if it's all connected. So this can still jumble around, bonds can be broken and that sort of thing. But for the most part, the iron particles will grab the fluid as they move around. And in doing so, what you get is a material that literally is attracted to a magnet. a fluid that attracted to a magnet without breaking out into constitutive parts. And that's really surprising in how it behaves itself. For those of you in the video class, I can probably hand these back to you before I forget. For those of you in the video class, you'll have to rely again on YouTube to see this. But go ahead and put ferrofluid into YouTube and launch it. I have a vial here that I'm going to pass around. In fact, let me go ahead and do that since we're running out of time here. I got a neodymium rare earth element magnet. Be very careful with this. Don't destroy watches. And then bring this to the bottom side of the ferrofluid. Do not open this container. This is like one of the most staining fluids on Earth. You will create the world's biggest mess if you open this. And don't shake it around too, because the ferrofluid kind of obscures the view through the glass because it's really staining. But go ahead and see what happens when you bring this close to the bottom and then pass it to your neighbor.
What fluid is that?
This is called a ferrofluid. You can get it online for like $20.
No, does it have another name?
Oh, no, that's an iron-based ferrofluid. So it's just ground up iron particles.
Professor, what is the particle that holds the oil on the...
Oh, that is a surfactant. Surfactant. And what's interesting is that when you apply a magnetic force with a strong B field coming out the top to a fluid, now you have basically 3 forms of forces acting on the fluid. So you remember all the bar magnet experiment that you probably did in physics with the iron filings and the bar magnet. It has a north pole, it has a south pole, and your physics teacher lied to you and said, oh yeah, you put your north, your south there, and you can see the flux lines because the iron filings kind of zipper up along flux lines. Well, we should know in this class by now that there's no such thing as a flux line for this kind of magnet. There is a flux density. And the reason why you see lines when you do this experiment is because the iron particle, which has mu sub r greater than 1, conducts flux inward when it's in the presence of a magnetic field. So where's the strongest magnetic field? Well, it's here and it's here. So the next iron particle will align itself there and conduct the flux accordingly. And so effectively, by just throwing your iron filings down, those filings will zipper up and resolve flux lines that aren't actually there. What is really there is a continuous flux density. So you get this zippering effect, and that's what you're actually seeing making the flux lines in that experiment. Now, when you go to the fluid, you actually have 3 forces you have to worry about. One, your iron particles want to zipper up. They want to follow the flux lines around. So there's this force to turn into discrete lines because of this zippering phenomenon. That's force number 1. Force number 2 is you have gravity trying to pull it back instead of zippering up. And then the third force is surface tension, which wants to minimize the surface area of the fluid. So those 3 forces, as you'll see when you pass this around, make this weird spiky pattern on the fluid. The magnetic fluid starts to zipper up. It gets pulled down by gravity, and it kind of gets smoothed out in between in the valleys because of surface tension. And depending on how far away you hold that magnet, you get a different pattern. In fact, the number of peaks is roughly equivalent to the flux density that you impress upon the fluid. So you can actually see the flux lines trying to form on that fluid. Try not to go above it because that dirties up the sides. Only go below the container so that the next person can see through it. So that's a ferrofluid, and these have very interesting properties. There's a whole kind of related compound of fluids. One of the neat things about this is that you can control the viscosity of a ferrofluid in similarly constructed compounds by impressing a DC magnetic field. And so has anybody seen those like on real high-end cars? I think they've even advertised it in the commercials. Some fancy magnetic suspension system.
Yeah, Mercedes.
Yeah, they're putting a fluid like this in the shock absorber, and by impressing a magnetic field, you're actually controlling the viscosity of the fluid in the shock absorber. So if you need a stiff shock, if you're going to high velocities, you want to get a good feel in the car, you impress the field and you stiffen it up. Then you relax it when you're in slower, or vice versa. I don't know. This is why I'm not a car engineer. I'm not a mechanical engineer. I don't know whether you want high viscosity or low viscosity in a shock absorber at different speeds. So any questions so far? You can also find these at use in a lot of high-end audio equipment because you could pack a magnet with this fluid and you wouldn't lose any flux. Anybody have a speaker that has ferrofluid in it? And again, tends to be only in high-end pieces of equipment. But the idea is that, you know, speakers heat up, especially if you're driving them, especially the way you guys drive them, you know. They heat up, and you would like to have a fluid that conducts that heat away like a good fluid does with convection. But you'd also like to have a magnetic fluid that conducts flux and keeps it confined to your speaker and maximizes the head banging that you can do. So that's another use of the ferrofluid. Actually invented by NASA, I think, in the 60s, when these gee whiz things are like, oh, how are we going to use that? And eventually found its way into some interesting applications. The most important, which I think is probably freaking out high school physics students and getting them interested in science.
You know, they make cascades of fluid and like such the electric field that they put, like they make flowers.
Oh, really? Can you get it to? I would always like to be able to freeze a ferrofluid in a certain state, and I've actually been able to do it once, but not in a cool pattern. I haven't tried that.
Yeah.
But you know, that's an oil-based compound.
I mean, the thing is, it's keep flowing, but it looks like it's almost solid, but it's.
Oh, I see. So this stays in the fluid state, but you put magnets in.
Exactly. So it stays in that flower, but the flower section moves, but when you dry, it's solid.
Yeah, that's good. That's good. So if you ever want to make a solid ferrofluid, one of the things I found is that there's this compound you get in art stores called liquin. Anybody ever play with liquin? Do we have any oil painters here? If anybody's familiar with oil painting, oil paints take, what, a couple weeks to dry, right? Depending on the scenario. Because they're not actually drying, they're setting up ligands in the oil. There's this compound you can mix in with oil paints called liquin that will dry in like less than 24 hours. And because that's an oil-based compound, if you mix in liquin, you can actually freeze the ferromagnetic fluid in a solid state. I have never tried to freeze the pattern, though.
Does it affect the quality of the painting, though?
It depends on what kind of liquid you use. It can add like a little bit of a sheen that is a little unnatural to regular oil paints. But it lasts, it's long lasting. It's for impatient people. But usually if you're that impatient, you do acrylic painting anyway. Yeah, Brian.
How do you use what's the purpose of ferrite core on the end of a wire?
Oh, that's a form of shielding to keep certain high frequency modes of propagation off the transmission line.
Makes sense.
Yep. Okay. Well, good luck. See you Thursday for your test.